All right, in this video, we're going to talk about acids and bases. There are several different ways you can define acids and bases. An older historical definition was by Arrhenius, and he defined acids as something or a species that forms H+ ions, and conversely, a base is something that forms OH- ions. Now, as we'll see, there are other definitions of acids and bases that are really more useful. Let's just talk about this one because it kind of gets us started thinking about what an acid and base is. So an example using the Arrhenius definition would be something like HCl, okay, hydrochloric acid. So when HCl is put into water, okay, there is basically an equilibrium reaction that will occur that will allow the hydrogen of chlorine to come off, and typically it forms hydronium, H3O+, and then you get Cl-. Okay, now H3O+ essentially is equivalent to H+. Now H3O+, just to define this is called hydronium ion. And when Arrhenius was defining these bases over 100 years ago, or acids and bases over 100 years ago, H3O+ really wasn't a species that was known, but he defined them as H+. We now know that that's really H3O+. So that's an example of an acid. Okay, it's a species that basically can form H+ ions. An example of an Arrhenius base would be something like lithium hydroxide. If you put that into water, an equilibrium reaction occurs that basically allows OH- to form, plus Li+, and there's also water in there. But this is now the species that's formed. Now, the Arrhenius definition, again, is pretty simplistic and doesn't really apply well to a variety of acids and bases. So what we're going to see in a little bit a better definition. But before we get to that definition, let's just describe, in general terms, some strong acids and strong bases. All right, I'd like to list out for you some of the compounds that we would consider to be strong acids and also some strong bases. So strong acids are things like HCl, HBr, so hydrochloric acid, hydrobromic acid, HNO3, that's called nitric acid, H2SO4, or sulfuric acid. Another one would be H3PO4, or phosphoric acid. So those are things that basically can create a lot of the H+ or hydronium ions. Strong bases, these are typically going to be hydroxide salts, so things like sodium hydroxide, potassium hydroxide, oops, KOH, not KOK, sorry. So these are examples of strong bases. A couple others, magnesium hydroxide, MgOH2. Notice that this one actually can give up two equivalents of hydroxide. Another one that's like that is calcium hydroxide. And when we define strong acid and strong base, what we're essentially saying is that when these are put into water, they ionize approximately 100%. So they basically will break apart into their ions essentially almost all the time. We'll see a little later that there are examples of weak acids and bases, but this is just a simple list of some strong acids and bases. Now, a little bit more specific and, well, actually really broader definition of Bronsted-Lowry, of acids and bases is called the Bronsted-Lowry definition. And this applies to all different types of acids and bases, not the specific things related to the Arrhenius definition. So this is the definition that is really more widely used. So let's just take a look at what these are. So a Bronsted-Lowry acid is something or a species that donates H+. Okay, so it's going to give up H+, And a Bronsted-Lowry base is a species that accepts H+. All right, now that's related to the previous definition, the Arrhenius definition, but these are, I guess, broader and apply to much more, many more different types of species. So let's take a look at an example of this. Let's take a look at ammonia. Now, ammonia is going to have a lone pair of electrons on it and 3 hydrogens. So if I put this into water, and I'll draw out water like this, what can happen is that this species, the ammonia, with its lone pair of electrons, is going to come over and actually pull off a proton from water. As it does that, it's then going to break this HO bond. So what's set up now is an equilibrium where we would form this species, NH4 plus, which is called ammonium ion, plus OH minus. So in this case, the ammonia, okay, this is the H acceptor. So this is the base. Okay, so that, again, it's a species that accepts a hydrogen. So in this case, ammonia, it's accepting the hydrogen from water. So therefore, water in this case is going to be the H donor. So this is the acid. One thing I also want to point out is whenever you mix an acid and a base together, you get the conjugate acid and base pair. So if this is the base, ammonia, it's going to give its conjugate acid. Okay, so ammonium would be the conjugate acid of ammonia. All right, so these two are basically linked in the fact that they essentially have the same structure. It's just that this one has the extra proton put on it. Likewise, the acid that's involved in the reaction is going to give a conjugate base. And in this case, the base is hydroxide. So these two are linked. They have a very similar structure. It's just that one is missing one of the protons. Let's look at an example where we sort of flip the role of water. In this case, water is actually going to be acting as a base, and we're going to mix it with HCl, which is one of these strong acids. So here, water is going to be pulling off a proton from the HCl, and the resulting product will now be hydronium, which I'll draw out like this, and chloride anion. All right, so because water in this case is the species that's now accepting a proton, this is the base, and HCl is the species that's giving up a proton, that's going to be the acid. We can now identify the fact that hydronium is now going to be the conjugate acid of water, whereas HCl and Cl minus, these are related as the acid and the conjugate base. Okay, so those are two examples now of species that could be acids or bases, and you'll encounter lots of problems where you have to kind of identify which species is acting as the base, which is acting as the acid. So in general, we can then make an important statement. If you have a strong acid, when it reacts, it's going to make a weak conjugate base. Conversely, if you have a weak acid, when it reacts, it's actually going to make a stronger conjugate base. And in the next section, to finish up this video, I'm just going to list out some of the strong to weak acids and then show their conjugate bases as well. All right, so in this last section, what I want to do is just talk about a variety of different acids, and then we'll draw out their conjugate base, and then also kind of relate the strength of acids and the various conjugate bases. All right, so to start out, I'm gonna just run through these acids and then draw out what the conjugate base would look like. Okay, so in the case of water, the conjugate base would just be hydroxide. Okay, in the case of ammonium ion, the conjugate base would just be ammonia. Okay, now, so notice what's happening here. The acid, again, is a species that's going to give up the proton, and the conjugate base is that same species minus one of the protons here. Okay, the next one, carbonic acid. We'll give what's called the bicarbonate ion, HCO3. This species, CH3COOH, that's acetic acid, and its conjugate base is called acetate. HF, or hydrofluoric acid, its conjugate base would just be fluoride anion. Next, we have phosphoric acid, H3PO4. This would be the dihydrogen phosphate anion. Notice in this particular case, this actually has 3 potentially acidic protons. I'm just showing if one of those comes off. It turns out this is a polyprotic acid that could actually lose an additional 2 protons. We won't go into that quite yet. That'll be later in other sections. Hydronium, H3O+, its conjugate base is just water. Nitric acid, HNO3. This would be the nitrate anion. Next, sulfuric acid is also one of these polyprotic acids. I'll just show the conjugate base if one of those protons comes off. And then lastly, hydrochloric acid, its conjugate base would just be chloride anion. Now, I've listed these in a very specific way. Up here, these would be considered weak acids. And if I draw an arrow down going this way, these would be strong acids. And when we talk about the strength or the relative strength of an acid, what we're really talking about is the ability of these to give up that or donate that proton. So water, okay, not the greatest acid, whereas sulfuric acid, hydrochloric acid, these are quite strong acids and essentially will give up that proton in solution 100% of the time. All right, so this is increasing acid strength. As we go down this table. Now, recall in the previous section I mentioned that if you have a weak acid, it will give a stronger conjugate base. So over here, we have strong bases. And if we have a strong acid, like HCl or H2SO4, those give weak conjugate bases. Okay, so our trend is going in the opposite direction here in terms of the basicity of the conjugate bases. So this would be increasing basicity. All right, so that's an important relationship that kind of finishes up this initial discussion of the acids and bases. And you'll need to be able to recognize compounds that are considered to be weak acids versus the strong acids, and then this relationship, sort of an inverse relationship of the strength of the conjugate bases. So I hope that helps in our introduction for acids and bases. Good luck.